Question 1. Police use radar to detect speeding cars. A police officer stands at the side of the road and points a radar device at an approaching car. The device emits microwaves which reflect off the car and return to the device. A change in frequency between the emitted and received microwaves is measured at the radar device. The change of frequency is given by, and we have this equation here, where f is the transmitter frequency, v is the speed of the car, and c is the wave speed. The following data are available. Okay? 1. Explain the reason for the frequency change, and we have 3 marks for that. So the first mark will explain the Doppler shift. The Doppler shift is when relative motion between the source and observer causes a frequency shift. And then we want to relate it to this particular situation. So 2, the emitted frequency travels towards an observer that is travelling towards the wave. And then 3, this causes an increased frequency to reflect. That'll do. Sorry about this writing, it's very small there, isn't it? I haven't given myself enough space to write it. 2. Suggest why there's a factor of 2 in the frequency change equation. Well, with the radar we have a double Doppler shift. And we've talked about that in step 1. So in the first shift, we have an approaching car, and the frequency of the original microwave. And then the second Doppler shift is the reflected from the car, reflected from moving car. And the effect that has is waves reflect off moving vehicle, and frequency is further altered or further increased. 3. Determine whether the speed of the car is below the maximum speed allowed. Delta F equals 2FV over C. Let's rearrange for V. Delta FC over 2F equals V. Let's pop in all the data. 9.5 times 10 to the 3 times the speed of the wave, which is an electromagnetic wave, so it's 3 times 10 to the 8 meters per second. 2 times the frequency, which is 40 times 10 to the 9, and that gives us 35.6 meters per second. We're going to take that to 2 significant figures. We can see that the maximum speed allowed is 28 meters per second, so 36 meters per second is greater than 28 meters per second. Car is above maximum speed. Question 2. A train travelling in a straight line emits a sound of constant frequency f. An observer at rest, very close to the path of the train, detects a sound of continuously decreasing frequency. The train is. Okay, let's think of a person standing stationary. If there's a train coming towards it, emitting a constant frequency f, the waves are going to catch up with themselves. So what you would find is an increasing frequency or increased frequency if it's moving towards. So it's not A or B. We know that it's moving away, and the effect of the frequency is the frequency decreases because it's moving away from its waves. The fact that it's continuously decreasing frequency suggests to me that the train is increasing in speed to cause that frequency to decrease even further. So the answer is D. Question 3. Light from a distant galaxy observed on Earth shows a redshift of 0.15. Outline what is meant by redshift. Okay, we want to do the Doppler effect, but we want to do it in the context of electromagnetic radiation and the galaxy. So what we would say is the distant galaxy is moving away from the Earth. This causes the wavelength of the light to increase, and in brackets I'm going to put frequency decreases, and the light shifts to the red end of the spectrum. Question 4. A stationary sound source emits waves of wavelength lambda and speed v. The source now moves away from a stationary observer. What are the wavelength and speed of the sound as measured by the observer? Okay, let's do situation 1. We have, let's just say that's the sound emitter. And that's our observer. Everything's stationary. The wavelength is lambda and the speed is v. Situation 2, this source is now moving away, which means the wavelength of the waves increases according to the observer, but the wave speed always stays the same. The wave speed has got nothing to change in the Doppler effect, it never changes. So let's go to the answers. Start with speed. We know that speed doesn't change, so we can get rid of that and that, so it's got to be A or C. We know that the wavelength will increase in the second situation, so the answer is A. Question 5. The collision of two galaxies is being studied. The wavelength of a particular spectral line from the galaxy, measured from Earth, is 116.04 nanometers. The spectral line when measured from a source on Earth is 115 nanometers. A. Outline one reason for the difference in wavelength. And that's exactly the same answer as we've just mentioned above. The galaxy is moving away from the Earth. The light emitted by the galaxy experiences an increased wavelength, and in brackets I'll put the frequency decreases, which causes the light to shift towards the red end of the electromagnetic spectrum. That's probably more information is needed for 1 mark, but good practice to remember it all. B. Determine the velocity of the galaxy relative to the Earth. We're dealing with electromagnetic waves, which means we want to use the equation for redshift with electromagnetic waves. It's this one. We're not looking at frequency, we can take that out. And we want to find out what velocity is, so let's rearrange the equation. And we have all that data. The change in wavelength is 1.04 nanometers. The actual wavelength is 115 nanometers. And because this is going to be a ratio, we don't need to do times 10 to the minus 9, that's fine. Times 3 times 10 to the 8 meters per second, which gives us a value of 2.71 times 10 to the 6 meters per second. And we'll leave that in 3 significant figures because the least amount of significant figures shown in the data is 3 significant figures. Question 6. 2 lines X and Y in the emission spectrum of hydrogen gas are measured by an observer stationary with respect to the gas sample. And we can see the increasing wavelength is going from left to right. So the red end of the spectrum is here and the blue end of the spectrum is here. The emission spectrum is then measured by an observer moving away. So we know it's going to be redshifted because it's moving away. Which are the correct shifts X star and Y star for the spectral lines X and Y? We know the lines for X star and Y star are going to be on the red end of the spectrum, so they're going to be on the right hand side of the original lines. That rules out A and B, and now we have to decide which one, C or D, is the answer. Let me just take you to the formula for redshift when we're looking at electromagnetic waves. The change in wavelength is equal to wavelength, the original wavelength, times V over C. And assuming that it's moving away at a constant velocity, this is a constant. However, can you see that Y, the original Y, would have a greater wavelength than the original x, meaning the shift in y is going to be a greater value than the shift for x. You can see here that the shift in wavelength here is a smaller value than the shift in wavelength for x. So it's not that one. The answer must be C. Question 8. Outline how the light spectra of distant galaxies are used to confirm hypotheses about the expansion of the universe. So if we're on the Earth here and we see all these distant galaxies moving away from us, we assume that the universe is expanding. So how do the light spectra of these distant galaxies confirm that? Okay, easy. 1. The light spectra from the distant galaxies all show a shift in spectral lines towards the red end of the spectrum. 2. This shift suggests they are all moving away and the universe is expanding. Question 9 is higher level only. The reason for this is because we're looking at the Doppler shift referring to sound, and the sound equations for the Doppler shift are higher level only. An ambulance siren emits a sound frequency of 1200 Hz. The speed of sound in air is 330 meters per second. The ambulance moves towards a stationary observer, so it's a moving source, at a constant speed of 40 meters per second. What is the frequency heard by the observer? So we go to our data booklet and we've realised that it's a moving source equation. So the moving source equation is f dash equals f v over v plus or minus us. And we need to decide whether we're going to use plus or minus this us. Let me just draw a little picture here. We've got an ambulance. It's moving towards a source. The ambulance is releasing waves. Because it's moving towards the waves that it's recently emitted, we expect these waves to bunch together and push together and that observed frequency to increase. If we want this observed frequency to increase, then this ratio here must be more than 1. For it to be more than 1, the denominator has to be less than v. So we want to subtract the value of the source's speed to make sure that that happens. So f dashed is equal to f, 1200, times 330 divided by 330 minus 40. So that's 1200 times 330 divided by 290. So we're looking for something with a 290 on the bottom. That works there. The answer is D. Question 10. A train moves at speed u relative to the ground, sounds a whistle of constant frequency f as it moves towards a vertical cliff face. The sound from the whistle reaches the cliff face and is reflected back to the train. The speed of sound in stationary air is c. So we have, to begin with, a moving source, and that has speed us. It hits the cliff face and it reflects back, to which point we have, on the reflection, we have a moving observer. A speed of u(o) in the opposite direction. Okay? And we want to find out what whistle frequency is observed on the train after the reflection. We have 2 Doppler shifts. Let's take situation 1 where we have a moving source. We'll go to the data booklet and our equation for a moving source is f dashed equals f v over v plus or minus us. In this case, v is equal to c. That's the speed of the sound in stationary air. And because the moving source is moving towards the stationary observer, as in the last question, we're going to use the minus or the subtraction on the bottom. So it's c minus us. That's our expression as it moves towards the cliff face. After it's reflected off the cliff face, it becomes the moving observer. So we have another equation for that. That's f dash equals f v plus or minus u-o over v. And of course v is equal to c, so let's rewrite that. F c plus or minus u-o over c. Do we want a plus or a minus? Well, we want the frequency to increase because it's moving towards it, so it's going to be plus u-o. So let's just call that f1 dash and f2 dash. And of course, us is equal to u-o. Let's call them all u, because the train stays at a constant speed. Let's bear that in mind. Now, what we want to do is find out the resultant frequency from the moving source and then the reflection and the moving back. So we need to multiply f1 dash times f2 dash. That means we're going to do this. F c over c minus u times c plus u over c. These cancel. We're left with f c plus u over c minus u, and the answer therefore is A. If you didn't know that you had to multiply those factors and you thought, oh, maybe I should add them, which to be honest would be a natural thought to add them, then you're never going to get any of these answers. Okay, so you should have just thought, right, okay, I'm not going to add them because I'm not going to get an answer. Maybe I don't understand why, but you have to multiply those factors to get that stage. Question 11. A train is approaching an observer with a constant speed of c over 34, where c is the speed of sound in still air. The train emits a sound of wavelength lambda. What is the observed speed of the sound and observed wavelength as the train approaches? What we do know in the Doppler shift is that the observed speed of the wave never changes. So we're looking at A or C, not B or D, because that suggests that the speed changes. And let's have a think. We've got a train approaching a stationary observer. It's releasing waves and it's going to catch up with its waves. So we expect the wavelength to be decreased from its original wavelength. That means we need a fraction that's less than 1 of the original wavelength. So it's not C, it must be these two. The answer is A. Question 12. Source S produces a sound wave of speed v and frequency f. S moves with a constant velocity of v over 5 away from a stationary observer. What is the frequency if measured by the observer? So we want to know the observed frequency. We have a moving source, so we're going to go to our data booklet and come up with this equation. We know that the source is moving away from the observer, so we expect the frequency in that case to decrease. So our equation becomes v over v plus us. Let's relate this equation now to the question. F dash equals f. The speed of sound is v, but the speed of the source is v over 5. What can we do now? Well, v plus v over 5 is the same as v plus a fifth v, which gives us 6 over 5v. So let's put that into the denominator instead of that. F dash equals f v over 6 fifths v. These v's cancel out. So we've got f dash equals f 1 over 6 fifths, which takes us to f dash equals f 5 over 6. So the answer is B. Question 13. An ambulance emitting a sound of frequency f is moving towards a point x at a velocity of 40 metres per second. A car is moving away from point x at a velocity of 20 metres per second. The speed of sound is v. What is the frequency detected in the car? Okay, this is very similar to the question we did a moment ago. There's 2 Doppler shifts. The first is where there's a moving source and it's moving towards the observer. The second is where there's a moving observer and it's moving away from the source. And we have to take both of those shifts into account. So let's do number 1. F1 dashed is equal to, now we've done the moving source equation, which is f v over v plus or minus us. We We have to decide we're plus or minus. In this case, at x, we expect the frequency to have increased. So our f1 dash is if it's to increase, then this has to become a factor greater than 1. So it has to be minus. So v minus 40. That's our first Doppler shift. Then we look at the second Doppler shift where it's a moving observer. The equation for that is f v plus or minus u0 over v. And again, we want, in this case, it's the observer's moving away. We expect the frequency to decrease, which means that this factor has to be less than 1. That means we have to do f2 dash equals f subtract, it has to be minus, so v minus 20 over v. Just as we did in the last question like this, we have to then take these two shifts and multiply them. So we got f v over v minus 40 times v minus 20 over v. These two v's cancel, and we're left with f v minus 20 over v minus 40, and that just can be rewritten as, and the answer is A. Question 14. A train is sounding its whistle when approaching a train station. 3 statements about the sound received by the stationary observer at the station are. Okay, let's just draw this quickly before we look at these statements. We've got a train approaching an observer. It's releasing some waves, but it's going to bunch up because it's going to catch up with those waves. So we expect the wavelength to decrease, the frequency to increase, and the speed always stays the same with the Doppler effect. Okay, let's look at the statements. 1. The frequency received is higher than the frequency emitted. Yep. 2. The wavelength received is longer, no, it's shorter than the wavelength emitted. And 3. The speed of the sound is not affected. Correct. It's 1 and 3. The answer is B.